Good evening, everyone. Welcome to the live session 2. I hope I am audible to all of you. Yeah. So today we will discuss about steam power systems. Okay. So it is already 6:05. So let's start the session. So we will start with the quick recap of what you have learned in the session videos. So what is a steam power system? Okay. So you can see this in this figure. So a steam power system. So first you have to understand what is a power system. So power system or power, we will be talking about power cycle as well. So power cycle is a cycle which continuously converts heat energy into shaft work. Okay. uh, that is called as a power cycle. And in a power cycle where the working fluid is water or steam, that power cycle is called as steam power cycle. Okay. So, and apart from the cycle, including the subsystems and all accessories, the whole system is called as steam power system. Okay. So one thing is steam power cycle, and including cycle plus all accessories and subsystem, it is called as steam power system. Why steam power system? Because the working fluid is water, that is called as steam. Okay. So here you can see in this block, you can see here is the our actual power cycle. So initially, uh, in the boiler, yeah, in the boiler, the heat is supplied to the water, the working fluid. This working fluid or water takes heat uh, from the boiler, then it goes to the turbine. Here in the turbine, the work is supplied from the turbine, and then this working fluid goes to the condenser. Here, the uh, water or steam, when water leaves from the turbine, it is in the form of steam. So when it goes to the condenser, it loses some heat and condenses and convert into the water. And then this water goes through the pump. This is the pump, and the pressure of this condensed water is increased, and then it is again fed to the boiler. So this whole circle is a cycle. So the steam power cycle mainly consists of four parts. That is, one is first is the boiler where the heat is supplied to the water. The second is turbine, from where the uh, work is obtained from the steam. Then third one is the condenser where this steam is condensed into the water and loses some heat. And the last one is the pump, which increase the pressure of this condensed water and fed this condensed water, high pressure condensed water into the boiler again. So this is the cycle. And now again you can see in the boiler as well, fuel and air are uh, fed. So fuel, when the fuel burns, it gives heat to the water, and those combustion product or gases uh, emit through the chimney. And also you can see here electric generator. So the work that we receive from the turbine is in form of shaft work. This shaft work is converted into the electrical energy with the help of generator. And the third subsystem is cooling tower or this cooling system. So this cooled water from the cooling tower is circulated to the condenser, and the steam that comes out from the turbine is condensed into the water. Okay, someone asks a question. सो किस किस कंपोनेंट में एक्सर्जी ज़्यादा होता है? सो विकी, वी विल डिस्कस about exergy separately. Just let me finish the initial part of this recap. Okay, we will talk about that also. Okay, so the main cycle consists of four parts, that is boiler, turbine, condenser and pump, and other subsystems are also the boiler, the generator and the cool tower. Okay, so now let's discuss about the steam power cycle, that is the middle part of this. Yeah, so in a steam power cycle, as we discussed, there are four parts: the boiler, the turbine, condenser, and pump. Okay, so in this cycle, yeah. So when water goes inside the boiler, it takes heat Q1, receives heat Q1 from the boiler, and okay, so when we fed water to the boiler, it is at low temperature and high pressure. Okay, so when it goes through the boiler, it receives heat Q1 and it becomes high temperature and high pressure water steam. Then this steam goes to the turbine, and uh, the turbine work WT received, and this high temperature high pressure water stream uh, becomes high temperature low pressure steam or vapor. This high temperature low pressure vapor then goes to the condenser, where this steam is condensed into the water, so it becomes low temperature and low pressure water, condensed water. Then it goes to the pump, where a work WP is done on this condensed water, and the water becomes low temperature but high pressure water. So this is the whole cycle. In boiler, heat is supplied to this water. In turbine, the work is received. uh, in condenser, again a heat Q2 is uh, wasted, or the heat Q2 is uh, wasted to the cooling water, and then the pump work is done to raise the pressure again to the uh, water. Okay, so this is how this system works, and it goes through the full cycle. So this is a normal steam power cycle. Okay, so here we can see in the whole cycle, heat Q1 is supplied and heat Q2 is rejected in the condenser, and we receive WT turbine work, and also WP, that is pump work, is supplied to the system. So from the first law of thermodynamics, from the first law of thermodynamics, we can say summation of Q is equal to summation of W, and that is total heat transfer to the system is Q1 minus Q2. The Q1 is heat supplied in the boiler, and Q2 is the heat rejected in the condenser. That is equal to summation of work, that is Wt work, that is turbine work that we receive in the form of shaft work, and minus Wp, that is pump work. So this pump work is done on the system, so this is negative. Okay, so Q1 minus Q2 is equal to Wt minus Wp. And if we calculate the efficiency of this system, that is efficiency is equal to W net, the total work output, the net work output, divided by heat input, that is Q1. So what is W net? W net is Wt minus Wp divided by Q1 is the total heat input. So that way we can calculate the efficiency of this system. Okay, steam power cycle. Now this is a very general system. Now if we talk about Rankine cycle, okay, so this is steam power cycle, simple. And yeah, so uh, yeah, we talked about the general steam cycle. Now let's talk about the Rankine cycle. So in this general cycle, we talked about how this water goes through the boiler, then turbine, then condenser and pump, and what happens at every stage or in every process. So basically, here are four processes where the first one is the heat addition Q1 in the boiler. The second one is work done in the turbine. The third one is heat rejection in condenser, and fourth one is the pump in the pump. Okay, so if we consider these four processes, if we consider these four processes as reversible ideal processes, then it can be called as then it will become a reversible cycle. And yeah, it will become a reversible cycle. And if we consider this, the first process, that is from 4 to 1, you can see in this diagram here. Okay, so here from point 4 to point 1, this is a heat addition Q1 from the boiler. From 1 double dash to 2 double dash, or 1 to 2, or 1 dash to 2, that is our turbine work that we receive from turbine. The third one is from point 2 to point 3, that is heat rejection Q2 in condenser. And fourth one is from 3 to 4, that is our Wp in the pump. Work is done on the system. Okay, so if we consider these all four processes as ideal reversible processes, and if this first process from point 4 to 1, that is heat addition, if it is a constant pressure heat addition, and from 1 to 2, it is an adiabatic expansion. From 2 to 3, it is constant pressure heat rejection, and 3 to 4 is again adiabatic compression. Okay, so if these all four processes considered as ideal reversible processes, and these are constant pressure heat addition and heat rejection, and adiabatic expansion and compression, then this whole cycle is called as Rankine cycle. Okay, so Rankine cycle is an ideal reversible cycle where it consists of two constant pressure heat addition and heat rejection processes and two adiabatic expansion and compression processes. Okay, and these are constant heat addition at the boiler, constant pressure heat addition at the boiler, constant heat rejection in the condenser, adiabatic uh, expansion and adiabatic compression in turbine and pump respectively. Okay, so this is a Rankine cycle. And now, yeah, now if we consider uh, now let's do the analysis of this Rankine cycle. Okay, for analysis we consider control volume at each at each component like boiler, turbine, condenser and pump. So let's see at the turbine. No, start with the boiler. Let's see at the boiler. Okay, so in boiler what is happening is uh, water is going from this point 4 to point 1, and let's assume uh, the enthalpy of water at point 1 is H1, point 4 is H4, point 2 is H2, and point 3 is H3. So in the boiler water takes heat, uh, Q1 heat, and the enthalpy of this water becomes from H4 to H1. So we can easily write that Q1 is equal to H1 minus H4. Similarly for turbine, that is adiabatic expansion. So here the work received WT, the turbine work, uh, can be said as a change in enthalpy from H1 to H2. So it is H1 minus H2, that is a turbine work. Similarly for the condenser, again we can see that heat Q2 is being rejected and enthalpy is going from H2 to H3. So Q2 equals to H2 minus H3. Similarly for pump, the WP work is being done. So WP is equal to H4 minus H3. Okay. So uh, this is how the work and heat interaction results in the enthalpy change of the water in this Rankine cycle. Now, now if we calculate the efficiency of this system, so efficiency is equal to net output W net divided by total heat input, that is Q1. And again we can write W net is WT minus WP divided by Q1, and WT we can see from the previous slide, the turbine work is H1 minus H2. So we can write H1 minus H2 minus WP is H4 minus H3, and heat Q1 is H1 minus H4. Okay, so efficiency can be calculated uh, from the enthalpy values of this cycle. Now now if we see here, uh, yeah, so now if we see here in the Rankine cycle, the pump work, a component pump work is here from point 3 to 4. So in the pump, water goes in the form of condensed water, not the steam. So if we consider here the pump work alone, pump work, that is WP alone, okay. So in this process, what is happening? WP work is being done on the working fluid, and what is the value of work done, WP? We can calculate that, uh, the value of work, WP. So for this process from 3 to 4, it is an adiabatic compression. So again, writing the equation for it, that is Q is equal to dq is equal to du plus, okay, again this is an open system, so yeah, so we are already considering the control volume, okay. So in the control volume, we can say enthalpy H is equal to U plus PV. So change in enthalpy from point 3 to 4, because this pump work is being done from point 3 to 4. So enthalpy H is equal to U plus PV. So change in enthalpy dH is equal to du plus PdV plus VdP, okay. And uh, yeah, so yes, and this equation also can be written as TdS is equal to dH minus VdP. How? Because this du plus PdV can be written as TdS, okay. uh, if you are not getting it how this du plus PdV is written as TdS, then please go back and watch the previous video. We there we explained it very elaborately how this comes. So uh, here uh, here this equation becomes TdS is equal to dH minus VdP, okay. And again here, this is an adiabatic reversible adiabatic process, so it is isentropic process where ds is equal to 0, okay. So here we can write it as dH is equal to VdP. So pump work from point 3 to 4 is VdP, because that is a change in enthalpy, dH is equal to VdP. So from here you can see that pump work depend on the specific volume of the working fluid and change in pressure, okay. But here you can see, as water is coming from this condenser to the pump, so water is in the form of liquid, and the specific volume of liquid is very very less than the specific volume of steam, okay. So that way we can say that the pump work is very small because the uh, the input to the pump is condensed water, not the steam. Okay, so uh, please remember it. It will be useful when we will be. It will be useful when we will be solving the questions in the next few slides. Okay. So from here, it can also be said that this pump work WP is very less than WT, the turbine work. So this efficiency equation we have written here can also be written as efficiency neta is equal to or close to H1 minus H2, that is turbine work, divided by heat input H1 minus H4. It can also be written as this because here the pump work is negligible compared to the turbine work we receive. Okay. Yeah. So now till here we have talked about the ideal reversible cycle. So Rankine cycle is an ideal reversible cycle, but the actual vapor cycle is not the same. The actual vapor cycle consists of many irreversibilities. So it is important to see what are the irreversibilities in an actual vapor cycle. So here you can see when the working fluid flows from one component to other component, so there is piping loss. Okay, so the first uh, irreversibility is piping loss. Okay, so pressure drops when fluid goes from one component to this other component. So here you can see that the pressure at outlet of boiler, that is pressure P1 dash, is greater than the pressure at the inlet of the turbine. So where from this difference comes is the piping loss. Due to friction in the pipes, this pressure loss occurs. Similarly, we consider the expansion of working fluid in the turbine as adiabatic expansion, reversible adiabatic expansion. But in actual vapor cycle, there is some loss, that is shown as Q loss here, and due to this loss, the turbine work WT we get from turbine is less than the enthalpy drop from point 1 to point 2. Okay, so this loss is the heat leakage. Okay, similarly if we see in the condenser, so again apart from heat loss from this water, pressure drop is also there because of the piping losses due to the friction. So we can say here that the actual vapor cycle consists of irreversibilities. This is why it is also important to consider the irreversibilities in the actual vapor cycle compared to the ideal vapor cycle, that is a Rankine cycle. And in numericals we will see in the next session that how this irreversibility affect our work output, and what is the effect of this irreversibility on the efficiency of our vapor cycle. Okay, that we will see in the next session. For now, this is the summary of uh, the ideal vapor cycle and actual vapor cycle. And also yeah, one more important thing here is, so what is the difference between Carnot cycle that we talked about in the previous session, and between Carnot cycle and Rankine cycle. About Carnot cycle we talked about in the last session, and in Rankine cycle we are talking about here. Okay, so what is the difference? So both the cycle are reversible ideal cycle. Okay, in both the cycles the turbine work is ideal. uh, the turbine work is reversible adiabatic process. The heat rejection is constant temperature, constant pressure, uh, heat rejection. The pump work is same as reversible adiabatic compression, but the main difference is the heat addition. In the Rankine cycle, heat addition is at constant pressure, and in Carnot cycle, the heat addition is at constant temperature. Okay, so this is the main difference in heat addition. In the Rankine cycle it is constant pressure heat addition, and in Carnot cycle it is constant temperature heat addition. So what difference we get due to this? Let's see. So the Carnot cycle tells us the maximum efficiency we can achieve between two temperatures, two given temperatures, the working temperature. So one is the source temperature and the second is the sink temperature. Okay, but in case of Rankine cycle the heat is added at constant pressure and temperature changes continuously. So here in this first figure, that is, yeah, so from figure A we can see, so the cycle from 1 2 3 4 hour to 1, this cycle is a Rankine cycle, and from 1 2 3 4C to 1 again, so that is our Carnot cycle. Because in TS diagram you can see that Carnot cycle works between two temperature, the source temperature or sink temperature. That is, uh, those parallel lines are these are those parallel lines. Okay, but the Rankine cycle works, uh, so in the Rankine cycle works in between two pressures, not the temperatures. So here if we analyze this through this diagram, we can see that for similar output, or for similar heat rejection, here the Q2, the heat input in the Carnot cycle is more than the heat input in the Rankine cycle. What that means is the net work output, that is the difference of Q1 minus Q2. Okay, that will be larger for Carnot cycle compared to the Rankine cycle. Okay, did you get me? See, to reiterate it again, for similar, for the same heat rejection Q2, so Vicky, we are coming to that. I will explain it. So in this figure, see, for same heat rejection Q2 in Carnot cycle, the heat input is more compared to Rankine cycle. Okay, and W net we calculate as Q1 minus Q2. So for Rankine cycle and for Carnot cycle, the Q2 is same for both, and Q1 is higher for Carnot cycle and lesser for Rankine cycle. So if Q2 is same but Q1 is higher for Carnot, means W net achieved from the Carnot cycle is more compared to the Rankine cycle, and our efficiency is given as W net divided by Q1. Okay, so from here we can say that the efficiency of Carnot cycle is higher compared to Rankine cycle. So Vicky asked, efficiency will be less for Carnot cycle. No, Vicky, the efficiency will be higher for Carnot cycle because for same heat rejection, the in the Carnot cycle the heat input is more compared to Rankine cycle. Okay, so the total or net work output uh, from the Carnot cycle will be higher compared to the Rankine cycle. So that way, the efficiency of Carnot cycle is higher compared to the Rankine cycle. Also, also in figure C, we can see the same thing. Uh, the difference is the steam at turbine input is in superheated form compared to the figure A, and again the uh, efficiency of the Carnot cycle will be higher compared to the Rankine cycle from the same principle, as Q2 is same for Rankine and Carnot cycle. Now, one minute. Yeah. So now, in figure B, uh, again we can see that the Carnot cycle is working between two temperatures, that is the temperature at 1 and 4C, and the second temperature is at temperature at point 2 and 3. So again the uh, efficiency of the Carnot cycle in case B will be similar to the efficiency of Carnot cycle in case A, the same, because the working temperatures in both the cycles are same. So it can be said that the efficiency of Carnot cycle will be higher compared to Rankine cycle in all the three cases. The one is uh, when the uh, steam is in saturated steam form at turbine input. The second one is in superheated steam, and the third one is also when uh, the first one is saturated steam. The third one is superheated, and the second case is when we receive steam as in saturated state at the boiler. Okay, so all these three cases, the Carnot cycle efficiency will be higher in the compared to the Rankine cycle. Okay, so this shows that the Carnot cycle efficiency is the higher limit that can be achieved when the when the working fluid is working between two temperature. One is higher temperature, and that is the second temperature is the local sink temperature. That is the limiting value of that sink temperature is atmospheric temperature. Okay, so yeah. So now, so this was the quick recap of the uh, steam power cycle. Now let's come to the questions. So the first problem is, which of these is not a major component of steam power cycle? Okay, before I go to the questions, Do you have any doubt till here? Anyone, any doubt? You can ask. Okay, so I assume you don't have any doubt. If you have any doubt, please uh, write in the chat box. Okay, so yeah, so the first question is which of these is not a major component of steam power cycle? The first one is turbine. Yes, it is a component, major component. The boiler is also major
कंप्रेसर कंप्रेसर होगा सर.
yeah. So turbine is a component. Boiler is also a major component. Pump is also a major component.
Yes sir. कीजिए ना मारा इसमें काफी पंप कंप्रेसर इज नॉट
But
a major
compressor
component.
is not a major component. So the answer is compressor. Okay. And yeah. So the next question. Actual cycle efficiency is calculated because of the thermodynamic irreversibility in the processes. So we talked about it that compared to the ideal cycle, in the actual cycle there are many irreversibilities in the form of friction in the pipes, the heat loss in the turbine, and heat loss in the pump itself. So considering all these thermodynamic irreversibilities, actual cycle efficiency is calculated. So the answer is true. Yes, actual cycle efficiency is calculated because of the
True, true.
irreversibilities in this processes. Okay. Now the third question is the processes associated with the ideal Rankine cycle are. So so which are the processes associated with ideal Rankine cycle? So we talked about it. So in ideal Rankine cycle, uh,
D D D D.
yes, yeah, yes, Vicky. So so if we see, so boiler, turbine, condenser and pump. So we discuss about it that from in the boiler uh, it is constant pressure heat addition. In turbine it is reversible adiabatic expansion. In condenser again it is constant pressure heat rejection, and in pump it is reversible adiabatic compression. So in the ideal Rankine cycle we have two constant pressure process and two isentropic. So reversible adiabatic process is an isentropic process. So let's see option 1, two adiabatic process, two isentropic. This is wrong. Two constant volume, no, no constant volume process. Two constant temperature process, no, it is also wrong. Two constant pressure process, two isentropic process. So the option D is correct. Okay. So yes, Vicky, your answer was right. Okay. So let's move to the next question. Yeah. So the ratio of the pump work input to the work developed by the turbine is. Yeah. So in the summary, we talked about. We didn't talk about the work ratio. So uh, in a typical turbine, we put the working fluid receive heat Q1 from boiler, WT that is turbine work we get as in shaft work from the turbine, Q2 heat is rejected in the condenser, and WP that is pump work is done in the pump. Okay, so there are two terms. The first is uh, work ratio. So work ratio is defined as W net divided by W T. Okay, so what is W net? W net is W T, that is turbine work, minus W P divided by W T. Okay, so one parameter here is work ratio, that is RW. Again writing it, WT by WT 1 minus WP by WT. So RW is equal to 1 minus WP by WT. Again here, this WP by WT is also defined as RBW, back work ratio. Back work ratio is WP by WT, pump work divided by turbine work. So it is a uh, so yeah, so back work is defined as pump work divided by turbine work. So in the question what is asked is the ratio of pump work input to the work developed by the turbine is. So this is back work ratio. Okay, any doubt in this question? Yeah, Vicky, you are right. Okay, so let's move to the next question. So Vicky asked, work ratio is higher for Carnot cycle or Rankine cycle? So yeah, it's a good question. So in a Carnot cycle, let's go back to the uh, comparison diagram. Yes. So here you can see that in Carnot cycle and Rankine cycle both, uh, the WT is same. Okay, but
Sir.
if you see uh, pump work WP for Rankine cycle, it is from 0.3 to 4 R, that is smaller compared to the pump work in Carnot cycle, that is from 0.3 to 4 C. So for same turbine work, the pump work in Carnot cycle is higher compared to Rankine cycle. Okay, so now question is, work ratio is higher for Carnot cycle or Rankine cycle? So work ratio is pump work divided by turbine work. So this work ratio, okay. So sorry, you are asking about work ratio. I got confused. So for work ratio is net work divided by the turbine work. Okay. So for Carnot cycle, if you see in this diagram, the net work is WT minus WP, and the value of WP is higher in the Carnot cycle. So in this given case, in this diagram, the numerator will be lesser for Carnot cycle. So the work ratio will be lesser for the Carnot cycle in this given case. Okay. Uh, you got it, Vicky? Okay, so let's move to the next question. That is, in Rankine cycle, heat rejection obtained from the. So in Rankine cycle, where is heat rejected? Heat is rejected in condenser. Okay, so pump is wrong, condenser is right, turbine is wrong, boiler is wrong. Okay, so in Rankine cycle, heat is rejected in the condenser. So next question. In the ideal Rankine cycle, compression is the pump is isentropic. Yes, we have already seen that. Uh, we have seen in the Rankine cycle, the compression and expansion of steam in pump and turbine respectively is isentropic process. So the answer is true. Okay. Yes. Let's move to the next question. The next question is, which of the following is not a primary goal of subsystems associated with vapor power plants? Okay. So subsystems, as we discussed in initial few slides, so apart from the main cycle, others are the subsystem. So here is the question is, what is not a
Convert
primary?
electrical power to shaft
Yeah.
power.
Yes. So
Yeah.
what is a primary goal of subsystem? What is not a primary goal of subsystem? So convert electrical power to shaft power. No, we do not convert. Any subsystem do not convert electrical power to shaft power, but generator converts the shaft power to the electrical power. Okay. Provide condenser cooling water. Yes. So which subsystem provide condenser cooling water? That is cooling tower. Okay. So cooling tower provides condenser cooling water. Okay. Convert shaft power to electrical power. Which component converts? Generator. Okay. And supply energy to vaporize the power plant working fluid. Which component does it? Boiler. Okay. But there is no component that converts electrical power to shaft power. So answer is option A. Let's move to the next question, which is for a vapor power cycle with a turbine that produces 5 megawatt and a pump that requires 100 kilowatt. The back work ratio is 2%. So what is the back work ratio? Back work ratio RBW is equal to pump work divided by turbine work. What is pump work? WP is equal to 100 kilowatt or 100 into 10 raised to power 3 watt. And what is turbine work? WT is equal to 5 megawatt, that is 5 into 10 raised to power 6 watt. So what will be the back work ratio? 100 into 10 raised to power 3 divided by 5 into 10 raised to power 6, that is 1 by 50, that is 0.02, that is back work ratio. So if we convert it into percentage, so that will be 0.02 into 100, that is 2%. Okay. So for the given case, the back work ratio is 2%. So this statement is true. Okay. Any doubt in this question? Okay, let's move to the next question. Yes, the next question is, with higher back work ratio, the actual cycle efficiency will be less. So actual cycle efficiency is W net divided by heat input Q1, and W net is equal to W turbine minus W pump. Okay. Now the question is, with higher back work ratio. So higher back work ratio is WP by WT. So we can write efficiency N is equal to WT minus WP by Q1. And yeah, take Wt common, so we get 1 minus Wp by Wt, that is Wt by Q1 1 minus R back work ratio. ठीक है. So from here we can say
True.
yeah, for a higher back work ratio, if back work ratio RBW is higher, then this whole term will be lesser and the efficiency will be less. So with the higher back work ratio, the actual cycle efficiency will be less. So this is a true statement. Okay, for higher back work ratio, efficiency will be lesser. Now let's move to the next question. What it says is work output of turbine is blank than the work input to the pump. So as we know, as we already discussed in the initial few slides, that the work input to the pump from point 3 to 4 is much lesser than the work output from the turbine. Okay, so here work output of turbine is much higher than the work input to the pump, so option A is correct. Okay, so work output of turbine is much larger than the work input to the pump. Sometimes we even neglect the pump work to calculate the efficiency, as we saw in the initial few slides. Okay, so Vicky and Rakesh, your answers are correct. Okay, so yeah, this is all for today's class. If you have any doubt, you can ask. Okay, if you
No,
get
sir. No, sir. No, sir.
yeah, if you get any doubt, you can write those doubts and you can also ask in the next session as well. Okay, so
Okay, sir.
so if you guys don't have any doubt, uh, sir, is there any WhatsApp group for doubts? So there is no WhatsApp group for doubts, but you can ask your doubts in the discussion form of this course. Okay, you can put your questions there and we will answer you. Okay, some of the question will be answered there only, and if remaining, I will take those questions here in the discussion. Okay, Vicky. Yeah, so if you don't have any doubt, let's close this session and see you guys in the next session. Okay.
Sir. Hello, sir. Hello.
Yeah. Yes, Priyansh.
Sir, which one of the following statement is correct? Work ratio and efficiency of Carnot cycle is higher than the Rankine cycle. Sir, सही होगा statement है. Statement, sir. A. Work ratio and efficiency of Carnot cycle is higher than the Rankine cycle.
Can you type it, Priyanshu? In a Rankine cycle, consider the work done by turbine during steam expansion is this. Pump work to feedback water into boilers. The work ratio will be. Okay, so you tell me what is the work ratio here? You are in the discussion in this whole class, and I hope you get the answer for this question. You tell me what is the doubt. Priyanshu, are you listening me?
Yes, sir. Yes, sir.
Okay, so let's take your question. You are saying the work done by turbine, that is Wt, is 3500 and the pump work Wp is 1300. Okay. So you
Yes,
are
sir.
asking what is the work ratio. Okay. The
Yes,
work
sir.
ratio
Yes,
is
sir.
W net minus W net divided by
WT.
WT,
Yes,
and
sir.
W net is WT minus WP.
WP.
Okay. So
Yes,
that
sir.
is 3500 minus 1300 divided by
Okay, okay.
3500.
Clear, sir. Thank you, sir.
Okay.
Thank you.
You got it?
Yes, sir. Yes, sir. Got it, sir. Thank you,
Okay.
sir.
Okay. So any other doubt? Anyone? Okay. So let's close this session and see you guys in the next session. Okay. Till then, tata, bye bye.
Okay, thank you, sir.